Now, what is all this stuff good for? It was already understood by Pythagoras that squares are special because squares satisfy Pythagoras' theorem in any dimension that says that if I look at some vector x, where x is represented by its projections to the orthogonal basis. So it's an element of real numbers to number of dimensions, that in any orthogonal basis, the sum of the squares equals the square of the hypotenuse in any dimension. So the length of this vector squared, Pythagoras. This we very easily generalized to complex numbers, because once you realize that you can define the length of the vector in a complex plane by adding real and imaginary components together, where z is in C, then this immediately generalizes. And if you have a complex field, wave function, some set of complex numbers, which you compute by taking the complex vector and dotting it by its Hermitian conjugate, this again is just the sum magnitude square of each component, the components in there. So this, because Fourier transforms are just continuation. For discrete set, we have functions defined like this on orthogonal basis, because the Fourier basis is orthogonal. This immediately goes into complex analysis. And it changes the name. So the same thing is always called 1,000 different people's names. So now it's called Persival's, not Pythagoras, identity. In Fourier representation, meaning finite number of points, we have a matrix version of this identity. If I look at the complex field over d points on a necklace, and I take it as a vector multiplied by its Hermitian conjugate, that's called absolute magnitude of the thing square. I'm allowed to insert Fourier transformation, which, remember, in this simple case was just unitary matrix. So I'm allowed to put an identity if this is an n-dimensional vector, in which identity is represented by Fourier matrix, which is just matrix of roots of unity to the power of product of the two indices. So it's just full of roots of unity. Time Hermitian conjugate, that was 1, and he had a correct normalization, which was square root of n in front. You stick that in there, and you obtain Fourier transform of the vector, because that's what this thing does. And you find out that if you're interested in the magnitude of this field, which in quantum mechanics is called probability, in engineering it's called the energy of a wave or something, you can compute it in original coordinates, you can compute it Fourier components to get the same answer. That's called Persival's identity if you're on discrete Fourier sets. But we have found out that continuum makes much more sense. Now it's elevated to a theorem it's still an identity, but now it's a theorem. And for some reason, that takes, we have to go to 1910 to rename this thing. Forget Pythagoras. Oh, it's a theorem. And what it says is, you take a continuous function. Remember, that's a generalization of a vector on very, very, very many finely resolved discrete points. We multiply it by its complex conjugate if it's a complex function. And that's magnitude square of the function. But now the function goes from minus infinity to plus infinity. So that's why it takes a French mathematician to give you precise conditions when this number makes sense. We call it L2 integrable, linear, bilinear 2, meaning we're looking at squares. And now theorem says that if you do it in Fourier space, integrate over Fourier coordinates, and if you're a boring physicist, stick 2 pi just on the right-hand side, just to make it asymmetric when it's not, then you are doing the same measurement. Now, for us, it just means what we used here, Fourier transform. Is unitary transformation. Even in the continued version, here was demonstrably unitary. But if you do this as a practical person, so let's say you're doing in engineering, you have a signal. That signal goes into your spectral analyzer. You are, working in the studio, mixing good audio signal for, let's say, Gogol, Bordello, or whoever. And now it's called Rayleigh energy. So now it's a serious stuff. It's energy theorem. And what it says is that the total energy of a signal is the sum, and in continuum it might be an integral, but in real world, you always have number samples. Sum of the power per frequency, and then you have to weigh it by the sampling interval. So, that's the simplest consequence of unitarity of Fourier transformations. Used all the time. For example, I told you that if you have a million-dimensional state space, don't come to me with value of the height of a graduate student 7, because it's going to be, it'll be 6 feet divided by, 1,000 or something, the variance of the signal. So I tell you, no, don't do that. You have to average over all Fourier modes and give me a statement. And you say, but, what average? And I say, look, if you take velocity, square it, divide by 2, that's called kinetic energy. So do the sum here over all kinetic energy in all Fourier modes and come back. And, you get the reasonable number. And that's what Rayleigh did about 130 years ago. So visualizing what happens in a turbulent fluid, you visualize it by finding what the mean energy of the turbulence is compared to, let's say, how much it's burning heat, which turns out to be the same quantity but for derivative of the velocity. And then you give me that plot, and that's very informative. So that's used all the time.